Hi, welcome to CON302. My name's Jeremy Cowan, and we're here for the session Building a CI/CD Pipeline for Containers on Amazon ECS. My name is Cowan, I'm a solutions architect, and presenting with me today is Ajit Zadgaonkar from Edmunds, who's going to tell you all about how they're using ECS to help folks like you and me find the perfect car. So before we get to that, however, here's what you can expect from this session. First, we're going to establish a baseline by reviewing the definitions of continuous delivery, continuous deployment, and continuous integration. Once we get through that, we'll explore each of the stages in the pipeline and the ways that you can create automated CI/CD pipelines with ECS. We'll then have a look at a few reference architectures before I finally hand the baton to Ajit. All right, so let's begin. So it's useful to define a few terms that I'm going to be using throughout today's presentation. The first is continuous integration. Continuous integration is the practice that involves integrating your code into a shared repository multiple times a day. These check-ins are verified through a build process that allows you to detect defects in your code. Now, the idea is that by doing small, frequent releases, you eventually spend less time troubleshooting and more time building new features. Now, for teams that are doing iterative software development, continuous integration is really essential. Continuous delivery, on the other hand, is an approach that involves creating a deployable asset that can be released to different environments at any time, from test to staging and then on to production. So if continuous delivery involves building a deployable asset that can automatically be deployed to, say, a non-production environment, what's the difference between continuous delivery and continuous deployment? Well, under continuous delivery, a developer or a member of the development team usually determines whether that update should be pushed to production, whereas continuous deployment, the release to production happens automatically without explicit approval from a human. Now, this is generally done only after the update has passed an exhaustive battery of tests. Now, the graphic on this slide helps illustrate what we've been talking about here. You can see which phases of the development cycle are part of continuous integration, continuous delivery, and continuous deployment. With continuous delivery, there's a manual approval step or a gate before the update is released to the production environment. Now, the important thing here is the opportunity for getting fast, frequent feedback, which occurs throughout the development cycle. And it's this feedback that helps organizations adopt an iterative approach to development. So what problems does CI/CD address? First, it shortens your time to delivery because it automates the build, test, and deployment phases of the software release cycle. And accelerating your release cycle is especially advantageous in today's climate where disruption through innovative software has become commonplace. CI/CD reduces uncertainty around changes because the changes tend to be smaller and they've gone through an extensive battery of tests before they're released to production. Additionally, frequent check-ins and builds give you the opportunity to get near instantaneous feedback, which you can use to fix issues earlier in the release cycle. So all of that's great, but how do containers relate to continuous delivery? For starters, containers can be deployed quickly, and the reason for this is really threefold. First, container images are comprised of file system layers that get cached onto Docker hosts. And when you update a container, only the layers that have changed are pushed to the hosts. Now, pushing only the deltas rather than the whole image reduces the amount of time needed to push an update. Second, containers share the OS kernel of the host that they're running on, so they tend to be significantly smaller than virtual machines, and they start a lot faster because they're not running a full operating system. And third, all of your application dependencies and configuration are packaged in the container, so you don't need to spend a lot of time writing complex scripts to install and configure the application when you deploy a container to an environment. Now, Docker also allows you to apply tags to containers, which you can use to track a variety of things, such as the build version, the git hash, the stage that the container is currently in. The latest version of Docker's image manifest specification now allows you to separate an image's tags from the secure hash of the image's layers, effectively giving you the ability to update an image's tags in place. This gives you an opportunity to build automation that simply updates an image's tags when the image is ready to be promoted to the next stage in the development cycle. And your pipeline can look at these tags to determine which environment to deploy the container to. And then finally, containers run consistently when they're deployed across different environments, precisely because all of the application dependencies and configuration are packaged along with the container. Now, a common workflow for Docker involves three stages, essentially: build, test, and deployment. And adherence to these stages allows applications to quickly travel through the whole life cycle. It also simplifies the adoption of DevOps. From a build standpoint, Docker provides a standardized and consistent way to build containers using Docker build. This differs from traditional deployments, where you typically had to package an application before it could be deployed. For those of you who have worked with Docker before, you may have heard how containers are analogous to shipping containers. And I think it's actually a useful analogy, because before the advent of shipping containers, goods loaded onto ships in a particular order because the containers were of different sizes and shapes. When that was standardized with shipping containers, the order in which ships were loaded really became irrelevant because goods were now packaged in a standard way. So although Docker doesn't provide a built-in framework for testing containers, it's relatively easy to perform tests both inside the container and against the container, which we'll have a look at a little later in the presentation. Another nice thing about containers is that they're lightweight. That is, that they consume relatively few resources on your machine, so you can often smoke test your whole application stack on your laptop, which is really convenient as a developer. Moreover, once a container passes all your tests, it should run consistently as it's moved from environment to environment, because the artifact that you deploy into a testing environment is the same artifact that you deploy to production. And developers like containers because they insulate them from how services work and how they're deployed. Also, their builds effectively become a versioned container image that's easily transportable and deployed through a container orchestration service like ECS. Now, as you can see, the Docker workflow aligns really nicely with continuous integration and delivery. A typical CI/CD cycle is comprised of 4 stages: source, build, test, and production. The source phase involves checking in your code into a shared code repository like Git or AWS code commit. And during the build stage, your application code is compiled, and a Docker file is used to copy the compiled asset into the container using Docker's add or copy commands. A Docker image is then built from that Docker file and then pushed to a container registry like Docker Hub or the Elastic Container Registry or ECR. During the testing phase, you can perform tests that both run inside or against the container. And then finally, when you reach the deployment phase, it means that your testing is complete and your update is ready to be released to production. So let's have a look at each of the stages a little more closely. The source phase involves checking in your code into a shared code repository like Git or code commit, which is a fully managed compatible service from AWS. With code commit, all the files that you push to a code commit repository are encrypted using a KMS key for added security. Not surprisingly, it integrates with other AWS services like CloudWatch events, which you can use to trigger actions as code is being checked in to the repository. So for example, using CloudWatch events, you can trigger a function to do a build on a feature branch instead of waiting until that feature is merged into the main. And as of last week, Code Commit now supports pull requests, which you can use to integrate changes from other people on your team. You could also use IAM for assigning granular permissions to your repositories. And another advantage to using these source control tools is that they allow you to audit changes to your code over time. And of course, there are other solutions besides Code Commit that you could use here, like GitHub Enterprise and Bitbucket. So doing frequent check-ins a day is a core principle of CI/CD. This helps keep your change rate low, which helps reduce the overall risk associated with introducing changes. With fewer changes in each release, at least it's theoretically easier to unearth bugs before they get released to production. It also gives you an opportunity to get feedback about your changes relatively quickly and change course if necessary. As for best practices, consider storing your Docker file in the same repository as your application code, commingling them together. You don't have to evaluate which version of various repositories can be used together. Moreover, by keeping them together, you can rebuild any container version you may need at any time. If you're using a compiled language like Java, store that compiled asset in a separate versioned repository and then use Docker's copy command to copy the asset into the image at build time. Lots of build tools support this, like Jenkins, for example. And then finally, and this may seem overly obvious, but keep code for building your container infrastructure and your pipeline separate from your application code. AWS offers a variety of services to help you build automated CI/CD pipelines, including Code Build, which is a managed build service that compiles your source code. You can use it to run unit tests, and then create assets that are ready to be deployed, including Docker containers. We recently released a VPC endpoint for Code Build, which is important for customers who are using private source code repositories in their VPCs and don't want their traffic to traverse an internet gateway. That said, there are lots of other build systems aside from Code Build that you could use here, like Jenkins, which has a variety of plugins for integrating with different systems. Now, when you use Code Build, you provide it with a build specification. That build specification includes a list of instructions for building the asset. These instructions are divided into several phases. That can include instructions for, say, logging into a Docker registry and then tagging and pushing the container to the registry once the image is built. You could also run unit tests like Mocha as part of your build as well. And here's an example of what a typical build specification for a container would look like. During the pre-build phase, Code Build gets credentials for logging into the container registry. In this example, we're logging into ECR. Next, it builds and tags the container and then pushes that to a Docker registry during the post-build phase. So when building containers, there are a handful of best practices that you should or try to adhere to. The first is to tag output artifacts to source control revisions. In other words, tag your containers with the git SHA or the version generated by the build system. Try to avoid using latest or production tags, as these can mask what version is actually deployed and make it harder to roll back to an earlier version. Optimize your build by removing non-essential files from your containers, and you could do this by adding a Docker ignore file to the same directory as your Docker file. When you use Docker ignore, you're basically telling Docker which files and directories to exclude from the build, which will increase your build's performance. You should also try to organize your Docker file in such a way that the layers that frequently change appear at the bottom of the file. And also try to co-locate the build system with its artifact repository, so you don't have to push or pull data over long distances. And then finally, be sure to scan your images for common vulnerabilities. Docker's beginning to do this if you've looked at Docker Hub recently. And rebuild your container images when the base image changes. Testing allows you to verify application updates across a variety of different dimensions. For instance, you can do unit tests or load tests, integration tests, and so forth. Fortunately, testing a Docker container is not much more complicated than testing the application itself, because all the application dependencies are packaged with the container. The primary purpose of all this testing is to help validate application updates and preemptively discover issues before they're released to a production environment. Now, there are basically two types of tests that you can perform when working with containers. You can either run a test inside the container, or you can run tests in detached mode or outside of the container. To run a test inside the container, you build the container and invoke the test suite from inside the container. This can be accomplished by passing commands to a Docker to the Docker CLI during the post-build phase, as we saw when we looked at the build specification for code build. And then in this example here, I'm calling a script that I've copied to the container to run a series of tests. And then I could look at the output from that script to see whether the test was successful or whether it failed. Now, besides running tests inside the container, you often want to run tests against your containers. For example, when doing load or performance tests where you're playing back a set of transactions. This requires you to deploy the containers to a test environment where those tests can be performed. And as we'll see shortly, ECS is really well equipped to handle the deployment of your containers across a set of instances where they can be tested with tools like Selenium or JMeter or RunScope. If your application has external dependencies, and if those dependencies are environment specific, like say, for example, your service has a dependency on a database, and the connection string for that database changes from environment to environment, consider storing those environment variables in a key value store like the EC2 parameter store, or in a third-party solution like Console. And then write your application to fetch these key value pairs at runtime rather than hard coding them into your application. So now on to deployment and the eventual release to production. Deployment should be a repeatable process that produces consistent and predictable results. As we've heard, containers make deployments simple because of the container model. The container is effectively a standard box with a known set of dimensions that can be deployed by an orchestration service like ECS or Kubernetes or Mesos. None of these tools really care about what's in the container. What matters here is the consistent format that Docker provides. And when it comes to deployment, there are several different options, which we'll explore further in the upcoming slides. These include things like rolling deployments, blue-green deployments, and canary-style deployments. But before we look at deployment pipelines for ECS, there are a couple of concepts that are needing further explanation. The first is a task definition. So a task definition is a set of configuration settings for a container, or a related set of containers that are meant to be deployed as a unit. For those of you who have worked with Docker before, task definition is similar to, say, a Docker Compose file, in that it includes the names of each of the container images, along with things like memory, CPU, ports, and other runtime parameters for running the containers. Service definition, on the other hand, is a declarative set of instructions for running long-running tasks like an API or a web front end. It typically includes the name and version of the task definition, minimum and maximum number of healthy instances, as well as auto-scaling parameters. It could also include some information about the load balancer that's fronting the service. And creating a deployment pipeline for ECS typically involves updating the task definition with the latest version of the container image, followed by an update to the service definition to use the new task definition. Now, to help you get started building a CI/CD pipeline for running containers on ECS, several of my peers have built reference architectures that can be found on AWS Labs in GitHub. This reference architecture that you're seeing here builds an automated CI/CD pipeline using GitHub, code pipeline, code build, and ECR. When a change is pushed to GitHub, it triggers the pipeline. The pipeline fetches code from GitHub and then passes it to code build. Code build then builds the container from the instructions that are in the Docker file, and then pushes the Docker image to an ECR registry. And then in the final step, the pipeline calls a CloudFormation step that updates the task and service definitions, which triggers a rolling deployment of a new task across the cluster. And you'll see that I've also included Jenkins here to show that in addition to using code build, there are other options available to you. Now, there are several reasons why you might want to consider using code pipeline to orchestrate your container pipelines. The first is its deep integration with the rest of the CodeStar services, like code commit and code build. The second is its integration with ECS. So until recently, you had to use a CloudFormation action, or you had to develop a custom action to update your ECS task and service definitions. Now, for many, and I know this certainly is applicable for me, learning CloudFormation is a fairly long and arduous process, and it can hinder the rapid development of pipelines for ECS. So I'm happy to announce that Code Pipeline will be adding an action explicitly for ECS, which takes a set of input parameters like the URL and login credentials for a Docker registry, along with the names of the service and task definitions to update when a new container image is pushed to the registry. And our hope is that this will simplify creating pipelines for deploying services to ECS. Now that we've finished exploring how to build and test containers, let's have a look at the knobs that we have to control how your containers are deployed. When you create an ECS service, you specify a minimum and maximum number of healthy instances. And these values are used to control the number of tasks that are replaced at once. For example, say you've configured a service to run 4 instances of a task with a minimum healthy percent of 50 and a maximum healthy percent of 100. When you deploy an update service, ECS will terminate 2 of the 4 containers and replace them with 2 instances of the new task. Once those containers reach a healthy state, the remainder of the older tasks are replaced with the new version of the task. Now, be aware that when the scheduler deploys a new version of the task, your connections to the task are gracefully drained first before the tasks are terminated and replaced with the new version of the task. And to trigger a deployment, all you really need to do is call the update service API. And this can be done a variety of ways, directly through the API itself, or through the CLI, or through CloudFormation, or even the new ECS. Now, these next few slides illustrate what I was talking about. By manipulating the minimum and maximum healthy instances, you can control how many instances are replaced at once. So here in this example, we start with tasks instead of the 4 I used in my previous example. Be aware that by setting the minimum to 50%, you're reducing your service's capacity, albeit briefly, during the deployment. There's also a brief period when both versions of the service are serving requests at once, at least until ECS finishes deploying the new version of the task. We'll talk about how you can do blue-green deployments here momentarily. So once the connections to the old tasks are drained, the new version of the task is deployed, and it registers itself with the load balancer, bringing the service back to 100% healthy. Once the new task is in a healthy state, the remaining old task is then terminated and replaced with a new version of the task. So we've seen how the ECS scheduler performs rolling deployments of your tasks across the cluster. And while this works for a majority of use cases, it may not be suitable for all, especially if you want to ensure that only one version of your service is serving production traffic at once. This often requires a blue-green style deployment where the new version of your service is deployed alongside the old version, but not serving production traffic. Blue-green deployments have several advantages over rolling deployments, including the ability to test the new version without impacting production, and then quickly rolling back to a previous version when issues are discovered with the new version. This can usually be accomplished by manipulating DNS records or through the application load balancer, which we'll see next. So in this reference architecture, we show you how to perform blue-green style deployments using the application load balancer. In this scenario, we have two services, each with their own target group behind the same application load balancer, and we use the application load balancer's host-based routing rules to route requests to each version. When we're ready to promote the new version of the service to production, we simply swap the listener rules for the two target groups. Here you can see the different host-based routing rules for each of the target groups. The blue service is serving requests at example.com, whereas the green service is responding to requests at next.example.com. After we're done testing the green version, we call a function to swap the listener rules on the ALB, which starts sending traffic for example.com to the green version of the service. Once we're satisfied that the green version is working as expected, we can then kill the blue version of the service and its associated target group. And canary-style deployments are another type of deployment that it's useful when you want to divert a portion of your traffic to a new version of your service, either randomly or based on a user's attributes. Now, canaries are often employed to do A/B testing, where you're trying to identify changes to web pages that increase or maximize a particular outcome, for example, the click-through rate for a banner ad. Based on the results of your tests, you can either replace the current running version with the new version of the service, or you can keep the current version in place. In this reference architecture here, we leverage Route 53 weights to adjust the traffic flow from one ECS service to another. We start by deploying the green service alongside the blue service, each behind its own application load balancer. And then we use step functions to gradually transition the traffic from the blue ALB to the green ALB. If the step function detects an issue, it'll automatically roll back its original configuration. Now, if you'd rather not use these reference architectures or build your own solution, we have some great partners who have integrated CI/CD solutions for Amazon ECS, a handful of which appear on the slide. And I'd encourage you to visit them at the Partner Expo while you're here in town. And now that you've seen several of those reference architectures for building CI/CD pipelines for ECS, I'd encourage you to give them a try yourself. We welcome all feedback, of course, including issues and pull requests. You should also consider joining our Slack channel at amazon-ecs.slack.com. And with that, I'd like to introduce Ajit, who's going to tell you how Edmunds is using ECS to help folks like you and me find the perfect car.
Thank you, Jeremy. Hello, everyone. Can you hear me okay? Check. Good now? Cool, thanks. Hello, everyone. At Edmunds, we love helping people find the right car. I'm sure many of you have gone there. Those who have not, check us out. We have a lot of inventory for you guys out there. I am Ajit Zadgaonkar. I'm Executive Director at Edmunds. I manage infrastructure operations, production operations, and I also lead DevOps practices at Edmunds. So I've kept some information for you here. My goal is to give you as much information as you can grasp and build your own CI/CD. We have been doing CI/CD at Edmunds for over 5 years now, and we have learned some hard lessons. Hopefully, by sharing those, you can avoid some of the mistakes that we did. So a couple things here on the agenda, quickly giving you the context of who we are, what we do, what has been our journey into AWS, into clouds, our journey into containers, and how this all fits into making CI/CD a very efficient system for us. So some of the interesting numbers that I've collected for you here. At Edmunds, we serve about 200 million page views a month. We have about 20 million unique visitors coming to us every month. We have thousands of partners and franchisee. We have over 5 million active inventory at any given point of time on the website. Over 250 million unique visitors visit us every year, which means 59% of car shoppers, they visit Edmunds. So in all, about 6 out of 10 people we influence when they visit in their buying decision. Edmunds has been into clouds for a little bit. We started exploring virtualization back in 2011 with Zen. We started changing, we deployed our own private cloud. And then late in 2013, we started exploring AWS. We thought we'll be migrating over in 3 years fully. We are all in AWS customer, and we basically went into AWS much ahead of the time. By middle of late 2014, 15 timeframe, since then we have been serving all of our production traffic from AWS. And in 2016, we shut down our data centers, and as you can see there. So the reason is why many people ask why clouds, and some of the reasons are pretty obvious. The business growth has been really aggressive for us. Products we wanted to roll out much faster rate, so we can reach out to our end users for the demands that they meet. We also have a desire for doing rapid experimentation. So in the old school, getting hardware provision into data center used to take 6-8 weeks. And so all of that is gone. And also dynamic infrastructure changes. So even with auto scaling in our private cloud, we still had to invest a lot of capital into maintaining extra hardware. So that increased our ongoing infrastructure cost. We have a public case study out there. We are saving about 70% of our cost by going to AWS, those who are interested in checking that out. So then once we were into clouds, containers came in. And why containers? So first of all, it's immutable object. Once you build it, it will run same on your laptop, onto dev bench, workbench, or in integration environment, or in production. So there's a consistent behavior. When you're debugging, when you're trying to troubleshoot, it makes it easy. And deployments are super fast. To give us some understanding of what fast means, before containers, when we were serving artifacts on EC2 hosts, an artifact that would take about anywhere from 11 to 17 minutes to get bootstrapped, come and get ready to serve traffic, now takes about 22 seconds. So that's a magnitude of change when we look at faster deployment. The faster deployment also helps us with better HA. So if something crashed, another container comes up, and container management softwares are pretty good for that, and we are using ECS. Not only that, we are also using different placement strategies like bin pack and easy distribution. With all of that, we are saving about 30% plus cost by going to containerizations. We're using ECS as our container orchestration and management platform. So basically, we migrated all of our services. About 95% of our services that used to run on EC2 are now running on Docker and ECS. ECS is managing all the underlying infrastructure, deployments, auto scaling, all of that. Once the images are ready, they are put into ECR. And we use CloudFormation and OpsWorks to provision ECS cluster. OpsWorks is also helping us configure the logging, the agents, APM agents, or config rules. And then I would say, except a few exceptions where some of the core infrastructure, like Elastic and Mongo, everything else now we run on Docker nowadays. We also looked at a couple container orchestration platform. We are all in AWS customer. We didn't have a hybrid solution. We are not multi-cloud either. So ECS met our needs. It has automatic scaling. It has easy distribution. Scaling, I told you, it's pretty fast. And then it's very well integrated with other services. So in our case, it worked out pretty well. The downtime of the deployment that usually used to happen before CI/CD and container was pretty dramatically reduced now. The AMI upgrades that keep on coming in to improve the Docker new version, that is very easy with ECS as well. So now that we were in cloud, we have Dockers, we wanted to revamp our CI/CD to, let's see, to see if we can get even more out of our infrastructure. The need for CD was, again, faster feedback. I don't want to repeat what Jeremy said, but some of the important things are faster feedback, low risk, and how do we identify bottlenecks as soon as possible, as soon as the code is in. So those were primary drivers for us to do. This is a conceptual overview of what we wanted to do, and I'll get to in a couple minutes, next slides, where we ended up. So this was our overview of what we wanted to do with CI/CD at Edmunds. The idea was simple. As soon as you write the code, you check in, their automated routine should kick in, and then deployment should happen in a manner that does not impact the services. And once it's out there, how do we manage it? So there's a continuous feedback loop going in to the development wing. A little bit understanding of how we are structured on our infrastructure side. We are multi-CDN and we are multi-AZ, multi-region deployment. Nginx is sitting at the top, and then basically then different environments are in different regions that we serve traffic through. We also do latency-based routing. So people who are coming from different region, they're served from a different region. Now getting into some of the details of how our implementation is and what we needed to do before we got to a smooth experience on CI/CD. So getting a CI and CD part is easy. That's orchestration. You can plumb different tools together and you have a CI/CD pipeline working there. Some of the important concerns are, do I have a CI/CD that is really going to catch defects, that's going to prevent mishappenings in production? Would it deploy artifacts in a way that are graceful deployments? And when there are things going bad, then are they going to remove the bad nodes graceful manner so there is no user impact? So to be able to do that, we needed to work and do some heavy lifting to make our platform ready for that. So as you see in the picture, CloudFormation is used to provision the host, underlying host. So when the host comes in, we configure the logging there, we configure Docker agents, ECS agents, and then config rules. So there is a guarantee that all of host looks similar. We also use AWS Inspector just in case if we want to run the scanning for security purposes. Then we, as Jeremy mentioned, CloudFormation gets very long and very complex, so we ended up using a small tool. It's pretty much API that we trigger, so if a developer wants to deploy something, it's a little tool. They come and add different details and automatically creates the task, the service definitions, the auto scaling. So we are, instead of using CloudFormation, we are using that. Most of the templates we standardized. Something that Jeremy mentioned, containers. By standardizing, the whole shipping industry changed. We took that a little bit to the heart. What we did was, before moving to containers from EC2, we looked at all of our artifacts, different applications that get deployed, and we looked at them in different ways. One is what type of artifacts they are, whether they're Java, Node, or something else. Are they web app or they're standalone applications? They're back office or they're public facing. So all of those, and we came up with multiple templates. And for each application, we standardized. The idea was once the templates are ready, then the migration will be smooth. And that really worked in our favor. So by spending about a month in coming up, templatizing, logging, all of that, it was ready. And once we start migrating, we were up and running in no time. So I would highly emphasize those of you who are looking at migrating to containers, do invest in time and try to standardize, and that will help you a lot. We also use configuration by default. It's also known as config by exception. So our containers are environment aware. So if you run on your laptop, it knows that, oh, it's a laptop versus a managed environment. And based on that, we can invoke the database connection. So a production environment should connect to a particular database connection string or particular caching layer, and so is the different DNS settings. So that helps a lot at the development team. You don't have to worry about changing runtime properties. That's part of our templates as well. Auto scaling. Auto-scaling is important piece. Many consider this as an operationalizing aspect. I consider this as a CI/CD aspect. If even in pre-production environment, you cannot deploy an artifact in a way that you're going to deploy in production, then you're not doing the right thing. You want to be having the consistent behavior. So there's a little bit of nuance involved in auto-scaling. We tried different things, CPU-based, memory-based, and that served pretty well. But our services were fronted with ELBs until we migrated to ALBs. By the way, that's another really strong thing that you should look at. We are looking at realizing about over $100,000, but just by consolidating and moving to ALBs. So as soon as we started adapting to ALBs, we started getting new metric like target-based request count. So now we have the request count-based scaling. So if a particular container is getting more requests, then we scale based on that. We also have CPU-based and memory-based scaling, but they are in the backseat just in case if something is needed. And we also have schedule-based scaling. So you can have multiple combinations, and depending on the situation, one of it will take care of it, and that's what is happening in our case. The same configuration is deployed in our pre-production environments as well. That solidifies our testing. We can mimic the production behavior more accurately. The downscaling was a little bit of, it's pretty interesting there. And when you're managing ECS cluster or any Docker container cluster, you got to manage two types of scaling. One is the container scaling, second is the cluster scaling. So for the instance auto scaling, to make sure that anytime when we want a container to be auto scale aggressively, we are keeping a little bit of additional host in our cluster. That way we can very quickly scale up and not wait for EC2 instance to come up for that. When downscaling, let's say if you have a scenario when there's a step down and downscaling, the downscaling doesn't work very smartly. What it does is randomly it will pull up a node down, whether you have the oldest node or newest node, but it's not aware that I have a container running on it. So we needed to work a little bit to deal with downscaling nuances. In our testing, we were constantly seeing throttling. So what we do is we have a Lambda function that checks how many nodes in the cluster are there that have nothing running. Before downscaling kicks in, we do a termination protection on the nodes that are running, and then we allow downscale to happen. So basically, when downscale happens, it's killing only the nodes that are nothing, they have no containers running. So that saved us a lot of headache during testing time frame. We also invested in building a custom Docker build framework. So as I mentioned, there's templates. We have templates everywhere. Now each artifact has a template where you can mention what Java version you're running, how much memory you need, how much CPU you need. There are global settings like APMs and others. For the goal here was to how do we allow developers to focus on one area is how do you code well. If we can externalize all of those properties and keep it in the code, with the code, then there is nothing else that developer needs to do. So there's a lot of templatization that we do at that layer as well. Very soon, the problem was how do we have a registry where what application, what type of URL we want to serve. So we came up with our own, we are calling it a service registry, Docker service registry. With each application code, developer checks in the URL rules. As soon as the container comes up with those, it registers those URLs on EC2, and Nginx picks it up from there and refreshes it. So we didn't have to write another complex service and discovery layer. And it has worked out pretty well for us. Down the line, we are looking at replacing Nginx as ALB matures. So we are looking for that as well. Canary. So now we have quickly checking where we are. We are in cloud. We have containers going. We have CI/CD going. We have auto scaling managed. That didn't really make us happy. Only thing we could do was automated deployment with rolling deployments, or we do blue-green. But that's not really what we wanted to do. We wanted to have continuous deployment in all of our environments. A new application gets deployed, send 2-3% of traffic. If everything goes well, then keep increasing the percentage of traffic. If it's not looking good, then scale it back. So this is where we are at with Canary. We have unique Canary services. We name them stable and the new version. When the new artifacts come up, they by default go to the Canary version. And I'll show you another picture very soon. And then there is an automated increase or decrease of the traffic percentage. We also use a lot of data that we gather from our pre-prod and production environments, and we have built a little machine learning model on top of it that tells us more accurately the state of our artifacts and testing. So now tying this all to CI/CD back again, this is a standard merge request workflow. We use GitLab. And the idea here is each developer works in a feature branch. Once they're ready to check in their code, they check in their code. We use Jenkins and code build both. Thank you, Jeremy, for announcing. We are looking forward to now move to code build. In our observation, code build has been 40% faster than Jenkins when it comes to building Docker images. I'm pretty excited going there. So developer checks in the code, it goes to Jenkins. Jenkins builds a Docker image. Once the Docker image is ready, we have something called a sandbox environment. That's where it gets deployed. It's a stripped down version of our production environments where developers can show it to buddy of them or show it to product team when they're working on small changes. Everyone can look at those, and when they're satisfied, they've done enough testing, then they are ready to merge it back to the mainline. Once they merge it to mainline, then it gets built a new version, and then it is deployed to the integrated environment. We run integration test there, load test, we try to do scalability test, all of that. And then finally through Canary, it goes to the production environment. This model also allows us to have dev leads and all different reviews, architecture leads. They review all of the code when the code is already deployed in Sandbox. Our tool set, there are lots of tools here. Some of them are common and that Jeremy mentioned. On the Git, we use GitLab and code commit. We have Jenkins and code build. Docker registry is ECR. We use ops to provision our hosts. We have tools that we develop for ECS API so that we can save ourselves from CloudFormation. On the pipeline orchestration, we have Jenkins pipeline, Blue Ocean. We also use code deploy. We also use code pipeline as well. There's a lot of data that's coming in. All of our artifacts are constantly emitting data that we put into time series database. We have statsd style data emission, and currently we are using Wavefront. That's a pretty powerful time series database that has alerting and anomaly detection as well. And finally, we use VictorOps when things go wrong to alert us. So this is correct and today's representation of where we are with our CI/CD. So developers work in a feature branch. Once they are ready to commit in, the artifact gets deployed to Sandbox, and once it's ready to get merged into mainline, then it gets merged into mainline, then we deploy it to a dev environment. That's our first integration environment. We run lots of integration tests. Once those automated tests have passed, artifact is ready to get promoted to Q environment. That's where we do scalability testing and load testing. We use JMeter for that. And once it's qualified there, then in production, it opens up a Canary branch. So code gets deployed through Canary as long as on the left side, below the green dials, if Canary version shows improvement from the previous version, it keeps increasing percentage automatically. We use Lambda step functions to increase the percentages. And if something is not looking good, then it starts to gradually decrease it. Now, instead of cutting down straight away to 0, we gradually decrease it, so we know at what point it started to go bad. So in case if it was a scalability problem, then it goes bad at 60% traffic or 70% traffic, we can find what's happening there. As I mentioned, all of the data we store into time series database. The idea is to gather as much data and use it to build modelings. To give an example, if you're deploying an artifact, right when it comes up, it shows a different symptom. Maybe it's building the cache. Maybe it's not ready. It's cold at this time. Maybe the spring beans are not initialized well yet this time. and you might see more number of non-200, but it settles in a couple seconds. So we don't want Canary to immediately say, no, something is going wrong. So by collecting data, now we have a better understanding of what happens when we deploy something. So that's just one example. There are many others. You can see suddenly the number of connections going to a data store increases because there are more number of containers. That also gave us ability to look into how do we scale databases and what kind of provisioning we need. So I would highly recommend emit the data as much as you can and build modeling to make your CI/CD stable. Ultimate goal is you check in the code and not worry about anything else. And if it's failed, it will come back to your desk and it will alert you. In our case, we alert via all means, email, phone, Slack. When things go wrong, we alert developers all possible ways that something is not right at any time. This is a dashboard of Canary versus stable. So by emitting the data, we know now this is a stable version, expected behavior. When Canary is launched, we see them side by side. And there's anomaly detection enabled on it. When things are not looking good, it fires events and alerts. And if it's looking good, then we keep on increasing the percentage. So that has saved us a lot. Earlier, we used to monitor it, and then let's increase the percentage, let's increase the percentage. Someone had to babysit and monitor it. Now we don't have to. As you can see, the green line here in most of, not the graph, but most of the line charts, the green line is the new version, and it shows improvement. So in this case, it will keep going, increasing the percentage to Canary version. So that was a dashboard as a simple example, but we gather a lot more data. The idea is to use AI for decision making. Eventually, I think from DevOps, we all are going to move to AI ops, if that's a new term. But the goal here is not to worry about those and let your CI/CD framework take care of everything from your check-in and everything after that. So currently, we are using AI to find, track, and remove anomalies. We find them, and it gives us action items right there. Many times, we find those in QA. There are very few things that we uncover in production. And really have these deep learning data guide your decision making. So before we had all of this, we would have a lot of scalability and availability driven problems. I would call them a P1 type of issues where there is an outage and there are people impacted. We can't serve our pages to the web users. That used to happen about 1 every 2 weeks. And knock on wood that we are going strong 8-9 months without any. So that's the power of applying these tools and containerization, the right auto scaling policies, having right strategies for deployment, including packaging policies and distribution policies. Now, as I mentioned, orchestration is just one part of the puzzle. But to be able to do CI/CD to a place where it's successful, there are fundamental things that I believe are the true pillars of success. First is invest in better engineering practices, bad in, bad out. If you don't have a code that's really well written and well structured, the logic is wrong, then that's what is going to stall the CD. I hear a lot with many of my peers as well, we have a CD, but it's always stalled. It's not orchestration engine that's stalled, it's the code that's stalled, and we all write it. So make sure that you have a team that's investing in right engineering practices. The second is really respect the failures. Tools don't lie. And there's a lot of subjectivity when we look at, we try to find, no, it's failing because, and we try to reason it. I think instead of reasoning it, we need to find the reason why it's failing and invest in those. It's 360-degree monitoring, sorry, it's looking like 3600, and monitor everything, right, from hardware to software to code, everything. Also monitor how many times your code is being reviewed when you check in. Also monitor how many times you're testing the code, how many times you're finding the defect. Is there a coverage gap? That's going to make CD successful. Containerization is not going to make it successful. It's just add on to it. Measure baseline and benchmark. If you don't measure, you don't know if you're improving or not. Having Canary will not necessarily give you benefit if you don't have baseline and benchmarking that you don't measure. And then once you have the data, use AI as much, or ML, or simple algorithms, even I would say even simplest as anomaly detection, to find what's going wrong. So you don't have to necessarily worry about finding things at a later cycle. You can catch them much sooner. And most important, have commitment from everyone. Without that, a CD is not successful. So you want to have a product team and development team and operations team, everyone is on board, that the idea is once you check in, it goes faster and smoother and without any incidents. So that's all I have for you guys that I wanted to share. But in closing, the CI/CD, the way I look at it, the goal is, and the objective is to make sure there's a better developer experience, there is a feature rollout that's smoother. You want to make sure that you're doing it in a way that adds to your availability, and there's a rock solid DR built into it, and there's a maintainability in it. You shouldn't be having to waste any time in managing it. And in our case, we are saving about 33% of the cost, and it's simply working. Of course, we had to put in a lot of effort to get our framework in place. So that's all I have. I have 5 minutes left for us for any question-answer sessions. But before you go, don't forget to give us your feedback, and surveys are up there on your mobile app. So we'll take any questions if you have.